All right, our next topic, well, hey, let me go back for a second. I calculated the forces using Pascal's law. I put 20 newtons of force in, and I got 333.3. Hopefully when you solved the problem, you had exactly the same answer. So we can see that there's a huge mechanical advantage. I push 20, and I get 333.3. Pretty good. Okay? Now, our next thought is this. What about dynamics? When the water is actually moving inside a pipe or whatever, so instead of the static situation where we have everything closed in, all right, let's take a look at a pipe. And everybody knows this. For example, you go to turn the water on in your home, and whether it's the bathroom or kitchen, and the water comes shooting out of these pipes. Okay? Now, water enters the house, and typically the water pipes underneath the street that supply the water to the neighborhood are very large. So as we look through, as we enter the house, the pipes get smaller and smaller and smaller. So let's take a look at a couple things here. All right, now let's suppose I take a pipe, and this pipe is very large here, and then very narrow here as it comes into the house. So I'm going to use my karate expertise and go, chop, and chop off a slice of water. So here it is, this little slice of water. So as we imagine it going through the pipe, it's just some volume of water. So I'm going to call this volume V1, like so. Now, as the volume V1 flows through the hose, doesn't it actually end up in the smaller section eventually? So as it works its way towards this area, it's got to enter the small part of the pipe. Now, here's an interesting thought. Let's say, for example, I ask you, let's say you're washing the car. When you wash the car, the water comes out of the end of the hose. So if you think about it, how much water actually comes out of the hose compared to how much water goes into the hose? So I'm thinking about it, when I wash the car, where does the water come from? So as I spray the car back and forth like so, how many gallons of water I'm using on the car, at the other end, doesn't the spigot provide a certain amount of water as it comes through? Well, anywhere in the hose, isn't the volume of the water that's flowing through the hose going to be equal? Because whatever enters has to leave the hose, or whatever leaves the hose has to have entered the hose. Let's say there's a kink in the hose. That's what's happened. So you go to wash the car, and very little water flows out of the hose. So you go back and you wonder to yourself, well, I wonder what happens, how much water flows into the hose if very little of the water flows out. Well, when you think about it, the amount of water that comes out of the hose has to be equal to the amount going in. If more water came into the hose than left, wouldn't the hose start to get like bigger and bigger? And it looks like those cartoon characters that just get larger and larger and then you explode. So here's a fact. The amount of water entering, the amount of volume in that section of the hose has to be equal to the volume in any other section of the hose. Any more entering would make the hose explode, which makes no sense. All right, so if I'm looking here, this volume V1 is also equal to the volume over here, and I'm going to call this volume V2. All right, now, at some point in time, this water was this water, and I'm going to call this volume 2. Notice that I'm not using velocity here, I'm using volume. All right, now, this volume of water that moves entered this hose. Why does this one look so long and skinny when this volume looks tall and wide? So, well, let me think. Well, the volumes are equal, but one has a lot of height to it, but not a lot of width. This one has a lot of length, but it doesn't have a lot of height. Well, these two volumes are actually equal to each other. So we know that the volume of the water here flowing has to be equal to the volume that flows out of the hose, and we end up with this idea. All right, now, when we take a look at the actual volumes themselves, don't we have an area? I'll call this area on this side of the hose A1. And on this end of the hose, the area of this section, on the very end of this, is going to be A sub 2. Well, if we think about volume, doesn't volume have something to do with area times the height or the length? All right, now, let's watch the movement of this. So as this thing moves through the hose in this particular section, doesn't it move some length? So I'm going to call that the change in length, the change in the distance that this thing moved forward. And I'm going to call that 1 because that's on this side. Well, this one also moves. And if we look here, there's a change in its length. And I'm going to call that L2. Why does this one move so much more than this one? Well, if we look here, isn't the hose narrow? And if you've ever held your finger over the end of a garden hose, you know for a fact that the water comes out much faster because the length, that distance it travels is much longer, so therefore it must be going much faster. All right, now, when I think about the volume, isn't the volume of this equal to the area times this change in L here? So let me write this down. So I've got A1 times the change in L1, like so. That's the volume of that particular slice. And then on this side, we know it's equal to the area of this slice times the change in L2, which is how far this water traveled in the same amount of time. All right, now, just because I want to, I'm going to divide both sides by the change in time. Well, if I do it on this side over here, don't I have to do it over here on this side? And that's what I'm going to do. Now, if we look here, there's kind of a thing going on. All right, we look here, and if I circle this, and I circle this, what is the change in length, the change in the distance, divided by the change in time? Well, everybody knows the change in the distance divided by the change in the time is velocity. All right, so we've got ourselves a new friend. So we look here, A1 V1 is equal to A2 V2. Notice that I drew the V's very small. These are not volumes. This is velocity, lowercase v. So when I'm looking at this particular one here, this is how fast the water is going. All right, so what is this saying to us? All right, if we look here, if the area is large, if the pipe is big old pipe, maybe the ones underneath the highway, the velocity is going to be relatively slow. It doesn't have to move very far because the volume, if you look, it's very tall. It can take its little sweet time getting through the larger pipe. All right, now, on this side of things, the area, the cross-sectional area, the top, is very small. So we have a lot of movement of the water. So to keep the volume of water moving the same, this has got to move quite a bit. And that means that the velocity here is very high. So let's say, for example, you buy a super soaker. You still got one in the garage? All right, if you look, the end of the super soaker, how big's the hole? The hole is relatively small. What does that do? Increases the velocity. So when you take the super soaker, point it at somebody and shoot it, you get a nice stream of water and it's going relatively fast. That's exactly what you're looking for. If you were to take a syringe, for example, fill it up with water and squeeze it, doesn't it shoot out and then you end up with a large stream of whatever medication you were supposed to get? So as we look here, the trick is this. If I want to make it go faster, I make the pipe smaller by making this area smaller. So these two things are equal to each other, and this creates these higher velocities for our things. Make a note of it, put this down in your notebook, and that tells us exactly how fast the water is moving within the pipe.